Hello, this video will introduce relative risk and odds ratio and how they are calculated. Throughout the class, we have discussed comparing the occurrence of events between two groups. Studies can characterize these associations by using one of two statistics, relative risk or odds ratio. When evaluating a relative risk or an odds ratio, we are really trying to determine whether an association exists and how strong it is. When we talk about an association, think of it as a relationship between exposure and outcome, as we've discussed earlier this semester. There's an association when the risk among the exposed is higher than the risk among those who are not exposed. There are two components to your interpretation of a number. First is the actual number, which we refer to as the point estimate, and the second is the statistical significance, which is shown by the p-value and/or the confidence interval. Relative risk is used when comparing the probability of an event occurring to all possible events considered in a study. For example, consider the risk of developing lung cancer in those who are exposed and unexposed to secondhand smoke over a 10-year study period. Upon study conclusion, the 2x2 contingency table shown here is created containing frequency counts of events for two groups exposed and unexposed to the secondhand smoke stimulus. This table provides all necessary data to calculate the incidence of the event for both exposed and unexposed individuals in a cohort study. Relative risk is calculated by dividing the proportion of individuals who suffered the event in the exposed group, here it is A divided by A plus B, by the proportion of individuals who suffered the event in the unexposed group. Here it is C divided by C plus D. Using our secondhand smoke example, let's input some numbers into our 2x2 table and calculate relative risk. In our example, the risk of lung cancer in the exposed group is 0.92. This risk is divided by the risk in the unexposed group, 0.17, for a relative risk of 5.41. Relative risk provides a single number ranging from 0 to infinity, and there are three resulting interpretations provided below. When interpreting the relative risk, we consider 1 to be null. A relative risk of 1 means there is no difference between the two groups, and the incidence and risk in the exposed is the same as the risk and the incidence in the non-exposed. There is no increased risk and no association. If the relative risk is greater than 1, the incidence in the exposed is greater than the incidence in the non-exposed. There is a positive association or detrimental effect, also known as a risk factor, of being exposed to the stimulus. If the relative risk is less than 1, the incidence in the exposed is less than the incidence in the non-exposed. There is a negative association or protective effect of being exposed to the stimulus. Remember, the further the relative risk is from 1, the stronger the association. When you interpret a relative risk, remember to take into account whether the association is significant. This applies to the odds ratio as well. The relative risk will be reported alongside a p-value and/or a 95% confidence interval. If the p-value is not less than 0.05, or if the confidence interval includes 1, the relative risk is not statistically significant. This is true no matter how large or small the relative risk is. You may have noticed that I said you have all the information you need to calculate a relative risk when you do a cohort study. This is not true for case control studies. You cannot calculate incidence or risk in a case control study. Thus, you cannot calculate relative risk from a case control study. Why not? A case control study compares cases that have experienced the event and controls who have not, and then assesses whether each individual was exposed to a stimulus or not. In the example here, the researcher compared 300 people with cancer to 300 people without cancer. The disease rate is 50% just because that's the way the study was designed, not because 50% of people under 15 years of age have cancer. Thus, a case control study is retrospective. When relative risk cannot be calculated, like in case control studies, researchers will often present an odds ratio. Before I show you the formula for calculating an odds ratio, here's a reminder about the difference between odds and the probability. Relative risk uses probability of getting disease. Odds ratio uses odds, which is calculated as probability divided by 1 minus the probability. So if there's a 60% probability that I will win this race, the odds are 1.5 that I will win. So thinking in terms of odds and probability, the relative risk is the probability that an exposed person gets disease divided by a probability that an unexposed person gets the disease. The odds ratio is the odds that a case or person with disease was exposed divided by the odds that a control or person without disease was exposed. Remember that even though you can mathematically convert between odds and probability, it is never okay to calculate a relative risk from case-control study data. Odds are calculated by dividing the proportion of people experiencing an event by the proportion of people not experiencing an event. Thus, an odds ratio is a ratio of two odds, one for individuals exposed to the stimulus and the other for those not exposed to the stimulus. Here's the calculation for the odds ratio. It is the same as the cross product using the 2x2 table that we designed earlier. The calculation is A times D divided by B times C. Let's look at a real-life example. This is a case-control study of children with leukemia compared to children without leukemia, which looked to see whether history of parental smoking was associated with cancer. Here is the 2x2 table created, just as was done in the earlier example. To get the odds ratio, we divide the number of kids with parental smoking by the number of kids without parental smoking in the cancer group, for an odds of 0.43. This is divided by the odds of parental smoking in the non-cancer group, 0.29, for an odds ratio of 1.48. Notice that this is different from the relative risk equation because we don't use total exposed or total unexposed anywhere in the equation. Odds ratios can range from 0 to infinity. They have three interpretations identical to those presented above for relative risk. The rules for determining whether an odds ratio is statistically significant is also the same as with relative risk. Odds ratios can be calculated for both cohort and case-control designs. Odds ratios are used when comparing events to non-events, with its calculation depending on the study design. For example, consider comparing a group of individuals who developed measles to those who did not, and then determining whether they received all the recommended vaccinations. In a cohort study, the odds ratio is calculated by dividing the odds of experiencing the event in the exposed group, A divided by B, by the odds the unexposed group experiences the event, C divided by D. In a case-control study, the odds ratio is calculated by dividing the odds that cases were exposed to the risk, A divided by C, by the odds that the controls were exposed, B divided by D. Relative risk can only appear in cohort studies or possibly at times in randomized control studies. Relative risk and odds ratios are comparable in magnitude only when the outcome under study is rare, for instance, some cancers. This is because the results of the relative risk formula and odds ratio formula become more similar as the denominator gets larger and as the number of disease cases gets smaller. It is important to consider that odds ratios consistently overestimate risk when the outcome is more common, for instance in hyperlipidemia. As a result, relative risk should be used if possible, and caution should be exhibited when interpreting odds ratios. Additionally, don't assume that a case is a case-control study just because you see an odds ratio in the results. Odds ratios are very common in the medical literature for both case-control and cohort studies. They are the result of logistic regression, which is every biomedical researcher's favorite statistical method. This concludes the video.